along this direction because the trapping is very weak along this direction, right? The potential gradients, because the intensity gradients are weak, it's weakly trapping. They make a 1D gas. Does that make sense? Okay. Yeah, I threw in a bunch of technical stuff here because I think it's important to talk about. All right. Yeah.
Is the distribution, the Gaussian distribution depends on the polarization?
No.
No.
No, it's just intensity profile of a laser beam you make in the lab is just typically Gaussian. Yeah?
What is the effect of corrections to the rotating wave approximation on this traffic?
So for example, for most of the traps we make, the formulas I showed you are kind of wrong and actually get things rather wrong. And if you're a theorist and you're trying to calculate things for the experiments, you'll get it wrong. This is a correction of the rotating wave approximation. You have to add in this term here. This is the 1 over d tuning term. This is a counter-rotating term in the parlance of AMO physics, and that correction can be important for things like 1064 nanometer laser beams or 532 nanometer laser beams, both of which are used very commonly in experiments. Okay, and it could be a 10 or 20% correction, which could be rather important, because we know things in these experiments at that level. Okay, one other example, before I think I move on to another topic, if I remember what's in my talk, is again, pi polarization or linear polarization in the AMO sense, and large detunings. We can also make a thing called an optical lattice. For example, we can counterpropagate two laser beams. If they have the same polarization, they'll interfere. They'll make a standing wave. The intensity is oscillatory in space, which means the dipole potential is oscillatory in space. And that's exactly what an optical lattice is. All right, and if the light is red detuned, then the atoms are trapped in regions of high intensity, or the antinodes of that standing wave. And if it's blue detuned, they're trapped in the nodes. That's an optical lattice, and that's how it's made. Simple stuff. Okay, so there's another example. All right, in the interest of time, I'm going to skip over light scattering in these experiments and start talking about interactions. Okay, so are there any questions, more questions about trapping and manipulating atoms with light before I talk about how the atoms interact with each other? Because if this, like I said, the second lecture today is going to have a lot of stuff in it about light, shining light on the atoms, and if this is still confusing, I don't want you to get lost. Everybody basically good? Okay. So that's one incredibly important experimental tool is we shine light on the atoms, we can trap them, we can manipulate them. It's how we add disorder in most experiments. These atoms also interact with each other. And so let me take the remaining part of this lecture to talk about as much of that as I can. And talk about how they interact with each other and how you can understand that. And one thing I'll do here, and I'll do especially in my lecture later, is I'll talk about a lot of the caveats, the things that are not exactly true that we say all the time, because I am starting to wonder in many of these experiments how important these things are that are complications to the simple picture we tell you. Okay, so in most experiments where we work with these neutral atoms, alkaline earth atoms, lanthanides, they interact through two atoms will interact with each other through a collision. They collide with each other. So what does that collision look like? So here's two atoms separated by some internuclear distance. And those two atoms interact with each other through a van der Waals potential, a 1 over r to the 6th potential. That potential is deep if the electrons, the valence electrons in those atoms are anti-aligned, singlet state, and that potential is a lot shallower if they're in a triplet state. At short internuclear distances from exchange interactions or the Pauli exclusion effect, those atoms strongly repel each other. So between the two atoms, there is a potential, which is always attractive, which supports various bound states in it. Okay? The potential minimum occurs at a few times the Bohr radius. Bohr radius is a number that AMO physicists love because it's a characteristic scale for atoms. And for the singlet state, that potential is thousands of Kelvin deep. Kelvin's also a unit I like to use because I think in Kelvin. I mean thousands of Kelvin times kb. All right, so that potential leads to scattering or collisions between the atoms. All right, and everything I'm going to say is a way to understand this in a simpler picture, but this is really the interaction between the atoms. This is really where it comes from. Okay, so how do we understand this? So I won't go through this in too much detail so we can get to lunch on time. The typical picture which is used is the typical picture of quantum scattering theory. okay, or quantum collision theory. So in the end, what I'm going to get to here, where I'm going, is I'm going to write down the effective potential for interactions that you see in books and papers all the time. But I want to show you a little bit about how we get there so you can understand that, and understand also that this picture leaves out a lot of physics, which is really important, actually. All right, so the way we think about these two atoms colliding with each other is we imagine them, we form a probability amplitude for the atoms to be at some internuclear distance, and that probability amplitude comes in as plane waves and scatters as spherical waves. Okay? And when we do quantum scattering theory, the goal is to find the scattered wave. So we write down our probability amplitude to find the atoms at some internuclear distance as a plane wave, plus a scattering amplitude times some scattered spherical wave. And we do a partial wave expansion of the wave function as radial wave functions times polynomials and cosine of theta. And what we find when we do that is we can separate out Schrodinger's equation into an angular and a radial part, and that radial part has a centrifugal barrier in it. All right, this is going to be important to something I'm going to tell you. But this is kind of textbook physics, so I'm going to go over it pretty quickly and just give you the flavor of it. All right, so we can look up in Saccharai's textbook or many other textbooks how we solve this problem and various limits. One thing we can find pretty easily is that radial wave function for different partial waves. There's a partial wave number L there at large internuclear distances, and we find it has a sign-like dependence on the radius, and that there's a phase shift compared to the incoming wave. All right, so what's happening here? Well, we have this potential. We have incoming wave functions here. At long distances, they look like plane waves, so I've kind of drawn a plane wave schematically here. And at short internuclear distances, of course, the oscillation of this plane wave kind of speeds up because of the potential, right? It's like undergraduate quantum mechanics. So there's also an outgoing wave function, and at large internuclear distances, we know exactly what that has to look like, and that has to look like a sine wave because we have to conserve probability current. So all that there is in this simple version of quantum scattering theory is a phase shift associated with each partial wave that tells you how much that outgoing wave function is shifted in phase compared to the incoming wave function. All right, so we've got that phase shift, and that scattering amplitude we've traded off for this phase shift. Okay, so of course, the picture is a little bit complicated because there's all these partial waves, right? So there's an effective radial potential for L equals 0 or S waves. That's this one here. As soon as I introduce some angular momentum in that collision, angular momentum between the colliding atoms, for example, at L equals 1, there's a P wave, centrifugal barrier here. And the reason I brought this up and had to tell you a little bit about this because this is really important. All the experiments we do, remember I told you the characteristic scales are like 100 nanokelvin? Well, 100 nanokelvin is a lot smaller than the size of that P wave centrifugal barrier, which is hundreds of microkelvin. And so in the experiments we do, for the most part, we have only S wave collisions, only zero angular momentum collisions, L equals 0 collisions in these experiments. Okay? Because the probability amplitude to tunnel through the centrifugal barrier is very small when the energy is really close to 0 compared to this hump here. Okay, so at the temperatures we work, we have only L equals 0 collisions. All right, so we can just worry about the L equals 0 part here, and there's just this radial wave function.